Hello and welcome to another Common Core Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and today we're going to be doing Unit 10, Lesson number 8, on other types of regression. Before we begin, let me remind you that you can find a copy of the worksheet and homework that go along with this video by clicking on the video's description, or by visiting our website at www.emathinstruction.com. As well, don't forget about those QR codes at the top of every worksheet. I know I remind you about them every single lesson, but if you scan that QR code with your phone or with a tablet, it'll bring you right to the video that's associated with the lesson. Alright, so let's begin. So far, we've looked a lot at linear regression, or fitting data sets with lines of best fit, either drawn by hand or by using the calculator. On the other hand, today, we need to recognize the fact that there are other types of regression. Specifically, we can fit things with exponential graphs, and we can also fit things with quadratic functions, right? So just as a reminder about how those general graphs look, right? An exponential either is an increasing exponential, kind of like that, or it's a decreasing and flattening out exponential. Either way, what's true about exponential graphs is also true about linear, which is that they always either increase or they always decrease. On the other hand, quadratic graphs, i.e. parabolas, they have that tendency to either decrease and then increase, or increase and then decrease. Okay? There's many other types of curves that one can fit to data, but these are the three types that we primarily look at in this course. And they correspond to the three largest categories of functions in this course. All right, I'm going to clear this out, and then let's go ahead and play with this. To begin with, we've got a nice simple problem. All right, I think it's simple. Exercise 1 says, for each scatter plot shown below, determine if it's best fit with a linear, exponential, or quadratic function. Draw a curve of best fit depending on your choice. So take a look at letter A. I mean, letter A is a little bit tricky. You know, linear seems to do pretty well there. Exponential does pretty well. I definitely don't think quadratic does. For me, I would say that this is best fit by an exponential curve. All right? The reason being is that if I try to draw an exponential of best fit, it seems to fit the data quite well. On the other hand, let's say I drew a line of best fit, right? That's not so good. You know, that's not so good. So I don't necessarily want to go there, okay? So I'm going to go with the exponential. I think the second graph is pretty obvious, and the reason I say it's pretty obvious is that there definitely seems to be a trend of the data increasing and then decreasing. Linear and exponential don't do that, but quadratic functions do, right? And if I were going to draw a parabola of best fit, it might look something like that. All right. Letter C is very similar to letter A. A linear function might do an okay job, but because this thing decreases and then decreases slower, I would have to say exponential. So again, I'm not sure that's the best exponential of best fit. In fact, I'm quite certain it's not. If I'm going to draw an exponential of best fit, I'd like it to go through some of the data. And there we go, right? So this is a very qualitative problem, not a quantitative, but qualitative. In other words, I look at these graphs, I think about what they're doing in terms of behavior, and then I make my call about what the best model is. We're going to eventually have, in our next lesson, an actual number that tells us how good the fit is, but we don't have that yet. So it's all qualitative. I'm going to clear this out, okay? So pause the video now if you need to. All right, here it goes. Let's keep going. So, letter D. Well, letter D, and letter E for that matter, there's your linears, right? Here's a linear fit, maybe not the best one, and here's also linear. Right? An exponential, I don't think so, right? This data certainly, both situations more or less look like they're increasing or decreasing with kind of a set rate, you know, nice line of best fit there, maybe a nice line of best fit there. I like linear in those two cases. But the last one again is a situation where the data is decreasing and then it increases again. So for that, I'd have to say it's a quadratic of best fit. Right? And maybe that would be the best fit parabola. You don't necessarily need arrows at the end. All right? So mostly what we want to do is we want to recognize that there's different curves that fit data, not just linear. Although I must say in the scientific community, the first model you always probably think of to fit data would be linear, unless there's some reason not to. All right, pause the video now, and I'm going to clear out the text. All right, here it goes. So let's keep playing around with this idea. In exercise number 2, biologists are modeling the number of flu cases as it spreads around a particular city. The total number of cases, Y, was recorded each day X after the total first reached 16. So on day 0, we recorded 16, and then each day afterwards we recorded a certain number of flu cases. The data for the first week is shown in the table below. All right. Notice not every day is represented. We don't have the second day or the 5th day, right? Letter A says, use your calculator to find the exponential regression equation for this data set in the form y equals a times b to the x. Round all, whoops, where's my period there? Round all parameters to the nearest hundredth. Okay, fair enough. So we need to open up the TI-84 Plus. There it is. All right, and we need to enter this data into our calculator. So we've done this quite a few times, but let's do it together. Let's hit the Stat button. Let's go over to Edit. All right, let's go up. If there's data in L1, let's go up, highlight the L1, hit Clear. Let's go over to L2, go up there, highlight, hit Clear. All right, now I'm going to go over back to L1, and I'm going to start entering the days. So I'm going to put in 0, 1, 3, 4, 6, and 7. Check the data. There's not a lot of it, but check it. 0, 1, 3, 4, 6, 7. All right, let's go back up, and let's go over to L2, and let's put in 16, 18, 22, 25, 33, and 35. Again, step back, relax, check the data, make sure that it looks right. All right, now the question is, how do we get an exponential regression instead of a linear regression? So, same kind of deal, hit the Stat button, go over to Calculate, all right, and now start hitting that down arrow. You know, it's weird because exponential regression is one of the most common regressions out there, and yet on the TI at least, you have to go down quite a ways until you find it. But there it is, EXPREG, exponential regression. And just like linear regression, all we have to do is select it. That pops us back out to the main screen. If our data is in L1 and L2, which it is, we don't have to do anything else. We just hit enter. All right. The calculator does its magic. It gives us that generic form, a times b to the x. It then lists the value of a, and again, I have to do a little cheating here, which is 15.921, etc. It lists the value of b, 1.122, etc. But don't forget to write your model down. We need to round both of these to the nearest hundredth, so that's 15.92. times 1.12, all raised to the x. Be careful, all right, at least on the New York State Common Core exam, if they ask you for an exponential regression equation and you give them linear, they will literally give you 0 credit, and vice versa. So watch out for that. Make sure you're doing the right kind of regression. All right, take a look at B. Based on the regression equation, how many total cases of flu will there be after 2 weeks? Well, how do we use our model to do that? Pause the video now and think about it. All right, well, what they're giving me is the input, 2 weeks, right? 2 weeks is the input. So should I put x equals 2? No. That input variable is in terms of days. So after 2 weeks, our day is 14. So that's what we're going to put in, 15.92 times 1.12 raised to the 14th. That's going to give us 77.80, etc. But of course, the problem doesn't tell us what to round to because it doesn't need to. We're talking about the number of flu cases. That's got to be an integer, right? So we're going to make that into 78. 78 flu cases. Now, letter C. According to your model, by what percent are the flu cases increasing on a daily basis? This really goes back to how to interpret an exponential model. So see if you can figure this out. All right, well here it is, right? The B, which is 1.12, is the multiplier, right? And if you think back to the work we did with exponential functions in Unit 6, right, that's 1 plus 0.12. That indicates that they are increasing at 12% per day. 12% per day. That's a pretty vigorous rate, but disease tends to spread very quickly, so not really surprising. Hospital officials will declare an emergency when the total number of cases exceeds 200. On what day will they need to declare this emergency? Well, what tools do you have at your disposal that will allow you to figure this out? Pause the video and try to figure out what day they need to declare an emergency on. All right, well, there's lots of different things we could do here. We could guess or check. We could solve an equation graphically. Honestly, what we're really trying to solve is when 15.92 times 1.12 to the x, when does this equal 200, or really exceeds 200? So in a certain sense, we're actually trying to solve an inequality, right? We're trying to figure out when it's greater than 200. Now, the way that I like to do this is actually by using a table, okay? So, since we've got the TI-84 Plus already open, let's now hit our y equals button. All right, and what I'm going to do is I'm going to put my model into y1, and then I'm going to use a table of values to help me figure out when it exceeds 200. So let's do that. If we have any equations in y1 or y2, we should clear them out. There probably aren't any in there, but there might be. And in y1, I'm going to put 15.92 parentheses, 1.12 parentheses. I got to use that little caret button to put the x up in the exponent. We did that a lot back in Unit 6. All right, as always, check out the equation. Make sure it's correct. And now I'm going to go into my table setup. So let me do that. Let me go into my table setup. It's debatable where we should make the table start. Now, granted, we know at day 14 we're only at 78. So we're not at 80, we're not at 200 then, but maybe I'll make my table start at day 14. I'll start at that 78 cases point. So, and then I'll make my table go by ones as usual. All right, so start at 14, go by ones, and let's pop into the table. All right, and take a look, you can verify there at 14, we're at, 77.80, etc. And now I'm just going to hit down, right? I'm going to just keep going down until I hit the 200, right? Keep going down, keep going down, keep going down, and there we have it. In fact, if I wanted to provide evidence, if I wanted to provide good evidence that I'm doing it correctly, right, what I would do is I'd generate a little table. Okay, very simple table. Maybe I'd have x and y1. What I like to do when I'm preparing a table like this is I like to include some values right before it. So at 21, we're at 172 cases. I'm going to round these things. Well, I didn't have to round that one. At 22 days, I'm at 193, let's say rounded. At 23 days, I'm at 216. So it looks like on the 23rd day, right? The 23rd day, they're going to have to declare an emergency. Not quite on the 22nd, but on the 23rd. All right. Well, we don't need the TI-84 plus right now, so I'm going to put it away. And now I'm going to ask you to pause the video and write down anything you need to. Okay, here they go. So one more question. All right, exercise number 3. The cost per widget produced by a factory generally drops as more are produced, but then starts to rise again due to overtime costs and wear on the equipment. So the more that a company or more that a factory produces a particular item, the cheaper it becomes per item, cost per widget. But then if you produce enough of them, there's wear and tear on the machinery, you got to pay people extra because they're staying there until 3 o'clock in the morning, so then the cost rises, right? So letter A simply asks, why should a quadratic model be considered for this data set as opposed to a linear or exponential? Pause the video now and see if you can answer that question. All right, well, here's why. The outputs decrease and then increase, right? So in other words, a linear data trend will only increase or only decrease, and the same is true for exponential. But a quadratic likes to have it both ways. It'll increase, then decrease, or decrease, then increase. Now letter B, maybe I dismissed our TI-84 plus too quickly, says use your calculator to create a scatter plot of this data to verify its quadratic nature. So let's open up the TI-84 plus one more time this lesson. Excellent. So let's hit our Stat button, go into our Edit menu. Let's go up and clear out L1. Then let's go over, go up, highlight L2, hit clear, enter. Let's now, in L1, go back there. Let's enter 35, and then 88, 110, 135, 154, and 190. All right, let me pause for a minute, let you catch up, let me catch up. All right, make sure the data is correct. Then we're going to go back up, go over to L2. We're going to put in 9.32, 2.63, 1.42, 1.32, 2.12, and 5.50. Enter. Now, again, I'm going to give you a chance to catch up, check over your data, make sure that it's correct, okay, check each value. Now, granted, here we're just trying to create a scatter plot. Let's go into our stat plot. So let's hit second y equals. Okay, let's pop into stat plot 1. Okay, make sure it's turned on. Make sure that the stat plot is selected. My x list is L1. My y list is L2. Okay, make sure that's all right. I'll use the little square as my marker. All right. Let's pop into our window now. Okay, remember we want the window to contain as much of the data, well, we want the window to contain all the data, but in as little space as possible. So when I scan the x-axis, what I see is that my minimum is 35 and my maximum is 190. So I think I'll set x minimum to be 30 and I think I'll set x maximum to be 200. That'll work. Now in my y's, I see that the minimum is 1.42 and the maximum is 9.32. So I think I'll put in y minimum is 1 and y maximum is 10. Right? That should do it. It'll get all the data in there. One last thing. I remember in the previous exercise I had just graphed an equation, that exponential equation. I want to get rid of that. So what I'm going to do right now, even though I'm sitting in my window, I'm going to hit y equals, not second y equals, but just y equals. And I'm going to clear out that equation because it doesn't need to be in there anymore. In fact, I don't want it in there. Sometimes it'll give me an error. I'm not sure why. But it's all cleared out. I think it's time to hit graph and see what our scatter plot looks like. Let's do it. And there it is. And again, we did all of that work just to verify what we could basically tell, in our data, which was that this looks awfully quadratic. Maybe not perfect, but again, if I was going to now draw a quadratic of best fit, especially if I was going to draw one pretty poorly, it might look like that. Okay? So, pause the video and write down anything you need to, and then we're going to wrap up the lesson. Okay, here it goes. All right, so the main purpose of today was to expose you to the idea that you can fit bivariate data sets with something other than a straight line. In fact, very often, exponential models do a better job of modeling the data trends than linear. But that's all dependent on sort of the physical phenomenon that's going on. There are occasions when you also want to fit data with quadratic functions, all right? And there's many, many other types, some of which you'll learn in Algebra 2. For now, I'd like to thank you for joining me for another Common Core Algebra 1 lesson by eMath Instruction. Until next time, keep thinking and keep solving.